Okay, so this is then, so we have 4 lectures about robot arms. Last week was basic concepts, kinematics, dynamics, and actually the summary focuses on that. And that's relevant for the exam. And you have this little exercise about it. And today I'll talk about time generation, movement time courses. So that's what would be called movement planning. I'll do it in a somewhat original style that emphasizes the analysis of human nervous system. And next we'll talk a little bit about the physical mechanics and control, which will be like a mini textbook summary of that whole field. And then the final lecture will be by Lei Zhang on human motor control. And that's more like fancy interdisciplinary stuff. This year is also interdisciplinary because we'll be looking at contrast between biological motion control and timing and robot time. Okay, so in vehicle motion planning, where we talked about planning, that in that case, when we talked about behavioral dynamics, it was sort of the plan was sort of generated online, right? Interacting with the environment. That's a special feature. And I did not actually really address. So there's one approach to the dynamic windows approach that in doing so instantaneously takes timing constraints into account in the sense of estimating whether the vehicle is able to brake before collision and so on, based on some modeling. So that's one small form of taking the time structure into account. But we did not really take time into account. For instance, we didn't really address whether we arrive at the target in a particular time. So when you do interception, for instance, of an object, that wouldn't, our vehicles wouldn't intercept necessarily. They just go to the target. But if there's an obstacle that takes longer to get there, and if the target is moving, then they might have some problem, right? So that there wasn't any time there. In reaching, there is, certainly in human movement, there is an aspect of timing very often because there is maybe the expectation to arrive at a particular time at the target. Maybe more natural in reaching than in driving, you could imagine. So minimally, for instance, in a company, in a factory setting, in that there are multiple robot arms and there is the conveyor belt and so on. And so you want to plan that by this time that arm is done and I can start the next arm to do the next thing, or I can move the part along the conveyor belt and so on. And it might, in that sense, also be coordinated. That is, you might want to say, if that is at this time, that arm, then the other arm, should do it at some other time. And in autonomous robotics, and we'll come to that difference in a moment, interacting with dynamic objects, moving objects, and catching, so it will be obviously have some kind of timing. So I'll first say a few words about how timing is done in conventional robotics, so industry, non-autonomous robotics, to then point out how it's different in non-autonomous robotics. And this is in the textbooks I recommended. I think I might have the link. It's this, the pictures are from this book, which I recommend. It's also on the exercise sheet. And there's an online version of this, as you might have noticed. It's chapter 9, if you look that up. So again, I just do that very briefly because it's not really something we go in depth. So first thing you have to decide is whether you do the planning in which space do you do that. Remember there we talked about configuration space. There are mathematically equivalent representations of that. You can use the joint space, for instance, or you can use the end effector space in a non-redundant articulator. Those are equivalent. Sometimes we say articulator equivalent to manipulator, equivalent to robot arm for some reason. Like the speech articulators are an example of that. So if you do this different planning, then the kind of interpolations you will do when you do a time course from start to end will look different. For instance, you could have straight line in joint space, which then leads to a curved path of the hand in space, or you want to do a straight path in the hand in space, and then it's curved in joint space. And a straight line is easier to interpolate as a function, but write down in the planning code a function, so that you might choose which one you do. Humans actually tend to move their hand on relatively straight paths in 3D. And so it's more, whatever that means, right? But that's what they do, and we'll come back to that. There are, if you think about that more generally, this was a 2D toy example. More generally, you have to think about configuration space. I briefly hinted that there are these 6-dimensional vectors, the screw vectors that characterize the configuration as a whole, include orientation and position, and then so you're planning in that space. That is mathematically more involved. I'm not going to explain that. And then the time course generation is really just writing down a function of time, often as a polynomial of time, right? It's in a computer with g as a parameter, and then it has some way of metering out that time as to its step motors to actually approximately do that in time. And this is again based on controlling the robot arm so well that when you make sure that it tracks that desired trajectory very well. Now that's the classical approach. So it's very common to use polynomials. You can imagine these are polynomials with boundary conditions. The boundary condition would be, for instance, initially at a particular location and find at another one, and then the velocity goes from 0 to 0. And then actually more typically, you're asking the acceleration to be also 0, so that this here is also flat. So acceleration is initially 0, so it's somewhat smooth. That's why fifth-order polynomials are very common, because if you figure that out, you have enough equations to determine constraints to determine the coefficients of these of 5 things: a total movement time, initial final condition, and these 2 boundary conditions. There, in other cases, they do more ad hoc kind of things, really to make it to move faster. Imagine the polynomial kind of slowly increases and then decreases, or wastes time in a way. Humans actually have that. Humans have this very smooth, something called bell-shaped trajectory, the velocity profile, which is approximated as a Gaussian, actually, more so than as polynomial. So they have these kinds of velocity profiles. So in robotics, sometimes you want to do this optimally fast. So you think about a ramp, so ramping velocity up and ramping it, at the good acceleration, that the one that you like. And then you have to smooth those ramps a little bit, because you can imagine it's odd when you have these sudden accelerations. And, that's mostly now in proprietary software in these robot arms, hidden in the control. You just give in the constraints and it will generate the trajectory like that. And there are some variants where they take into account constraints, somewhat like the dynamic window approach. They take into account that there might be certain limits, depending, if you plan an end effector space, these limits could come from the joint angles, what kind of accelerations and so on they can do. And so they show up in your planning space in odd ways, some curves, which say that I can't go beyond that velocity right now, because that would require too much of a acceleration. I can imagine that can be the sort of thing that you can compute beforehand, before you move. All of this is, of course, based on knowing everything, right? In the classical robotic scenario, you know where you want to go, where you are before, the whole sequence is all programmed, right? So you expect the objects to, like on the conveyor belt, to be in a particular position at a particular time. So when you use this, you can see when that will be one of the critical issues in autonomous robotics, that you don't really know all of that ahead of time. It might actually change while you're moving, or while you're doing your previous movement, it might change for the next one. So here are a few examples how to do that in autonomous robotics. And there has been a long history of that. This, unfortunately, I didn't put the year. I think this is end of the 80s, early 90s. Koticek is a famous guy. Dan Koticek is now at the University of Pennsylvania. Has a real fun webpage. And so I think he was maybe the original inventor of that. This was invented by multiple groups. I don't know exactly who was first. So there's a whole community who think like that. And some of the people I work with in human motor control overlap with these kind of people. So he had a demo that was a juggling robot. This pedal, and it would be juggling. Actually, it was ball bouncing, or doing some interesting complex patterns, like with multiple balls. And it had an interesting, so ball bouncing, you have time. You have to hit the ball at the right time with the right inclination of the pedal, to keep it right and keep it within range. And he had an interesting approach to that. First of all, let me say, the control of the ball, that the ball stays in the pedal, was done in a conventional P controller, proportional controller thing. So it really just looked where the ball is and computed the angle at which you should hit it to keep it within bounds. So there was nothing special about that. The timing, that is when you how fast you're going to move to intercept the ball, was based on an idea that I just summarized very briefly. It's based on an idea that you have a model of the ball. The ball is as a rigid body that has a free fall trajectory, and you're building a equation for the pedal so that the pedal will generate a periodic solution, a limit cycle solution, in which the estimated ball was a parameter, so that you're essentially face locking to the ball. I haven't explained face locking yet. I'll do that a little later, but it was something like that. You write down an equation, the solution of which is a limit cycle. Limit cycle is a periodic attractor. So the attractor property is so that you, even if you're not, you have to update it because the ball is changing. And so with the attractor will mean that you're just shifting, the attractor will shift a little bit from cycle to cycle, and then your system will be attracted to the correct oscillator. It's not like Radnor polynomial. It's only one solution. If you're a little bit off, there's no prescription how to get back to the right time course. And here, the time course will change a little bit as the ball bounces a little bit unpredictably. And then you want to plan a new trajectory for that new position, and you're not right on it. And so you're going to attract that into your oscillator. Roughly speaking, I'll explain that more. So that was a very innovative kind of thinking. The limit cycle is a nonlinear dynamic solution, attractor solution that's periodic. That wasn't common at all. People just think of harmonic oscillators that end up being at a fixed point, being rusty. Quite innovative, and it became famous through the Reibert school. This guy, Mark Reibert, his son's German, was at MIT, who does these logs. And all the this is the Boston Dynamics. He founded Boston Dynamics and is still running that. He was originally an MIT professor. He had a famous hopping robot. This is the hopping robot. So it's a robot sort of analogous to the paddle. It's just the robot itself that jumps. So the robot had a leg, and the leg, just one. So one-legged hopper, jumping. And so it was a passive spring that did the actual interaction, and then you would always insert a bit of momentum so that it jumps up. And again, the control of the robot in the plane would be done by changing the angle at which this head hits the ground. You have a model of that in P controller, so to keep it in vertical bounds. And the main thing is to keep that rhythm. And again, there you have the model of the robot as a falling object, and that makes a certain trajectory. And now you're writing down an equation that is that equation of the falling body, but you insert another term in that equation, which makes a limit cycle. And that term is what you're going to actuate. So you make sure that the robot delivers that term to the equation. It's only approximately true, but because you design it to be a limit cycle, even if you're not exactly on that solution, you're going to be close to that solution. The same kind of idea. Again, you don't have to understand that fully, but maybe you get an intuition for that. And so they have done this. So Kocek actually has some general discourse about that. I think I'll skip that because it's a little bit too abstract. It's a very interesting thing where you don't have to think about the details. You can just think about sort of a macro state. But I think that leads a bit too far here for this lecture. I'm just saying here that there is more than just that idea, right? You have to do a lot of things right to get that right. You mentioned that then the leg has to sense that now it's engaged and has to insert some momentum to actually hop and so on. And so here I wanted to show you this video. I hope this works now. I have to move this over here. Oh, we have this. Sorry. We know these things, right? This is a video from Boston Dynamics. They have all these kinds of robots, and they're much more complex than that. But the core idea of how these individual legs make their motion is that kind of idea, a unit cycle that is just sort of keeping a rhythm. and it is no reacting. It's, can you imagine kind of mistreatment of robots. So here, for instance, the legs encounter terrain, and so they don't actually extend as much as planned, and then the limit cycle just adjusts to that. And we'll just try to keep something optical. They also coordinate that and say, make sure that the different oscillators on a certain phase, like coupling them. And that's, so the robot doesn't have a model of that environment, doesn't have a plan. So it's just reactive to what happens to the individual legs. The steering, by the way, is all, it's not automatic, like it's someone, the joystick, which directs the robot in different directions. So it's usually, there are many variants of business from the company, but not for that. Now, for instance, it's like making that periodic motion, and that periodic motion can update every time it is mechanically prevented from actually achieving what it's supposed to achieve. Okay. There's lots of videos like that on the internet. You can easily look at that. But, so that's one line of thought here. And again, to finish that is to say, this was all done because in autonomous robotics, you don't know everything, so you can't just plan that perfect time course to go certain places, right? You have to do it on the fly, and therefore you're solving the problem of a dynamic environment, of the environment changing, even just perhaps because your plan wasn't perfect, and so the deviation from that plan is like a change in the environment. It wasn't actually necessarily a change; it was just the plan wasn't perfect, right? But then it also gives you for free that you can deal with a changing environment. So much more demanding, but then also much more performant. This is not done at all in industry robotics. They will just repeat their movement, and if it's off, then it's off. It's going to destroy a lot of stuff before some observer turns off the robot arm and corrects the error. So it's very fundamentally different in these autonomous machines. Okay, so it's always been, I can, of course, others will lecture a whole course about this, and it's boring in the sense, now you have to figure out the details and the different approaches, and they have their advantages and disadvantages and so on. But conceptually, it's just that. So what I instead want to do is throw out a few concepts that can be used to think about such things, and these engineers actually, in part, are inspired by that or interact with that and use concepts like that. And these concepts come actually from human movement or animal movement. Most of it is the human movement. And so I explain this. I explain why are we even using that word time. You will not actually find what's usually calling timing. They call it maybe time planning or part of motion planning or velocity planning. So, and then I'll talk about what absolute is timing versus relative timing is, coordination, and then picture of a couple of oscillators. So this slide is from a paper that I'll actually make available as reading material, sort of review paper, and you can have a little bit more text around it. And so here's an illustration of absolute versus relative timing. And so let's first think about timing really in the context of a periodic movement. We'll see later that doesn't always have to be the case. So periodic movement timing will mean that you're generating a time course, and then you repeat that time course. And so the time course is, the absolute time of the time course would mean how well do you do that? So for instance, if your time course is to move within 10 milliseconds, or let's say 500 milliseconds, from beginning position to target, and you go back, target, and so on. Absolute timing is how reproducible is it? Is it always 500 or 510 or something like that, right? And so here's are two time courses that I drew by hand, but there could be like neural activations, and you will see that there are certain events here that we consider here should be the relevant events. For instance, when the threshold is pierced, here the activation pierces the threshold here at this location, and then there, here again, here again, here again, and so on. And so the time interval between subsequent piercings of the threshold will be the absolute time. And this is done so that that's quite variable. See, this here is shorter, and then it's a longer interval, which would happen when you look at some neural signals like that. So this would be very variable absolute timing. But the other trace here is actually a line. So you see here the threshold is pierced at slightly different times, also quite variable, but the relative timing, which would be where is this threshold piercing compared to the corresponding one, that's relatively small. amount, and every moment is quite small. And that is what we call relative timing. And so this is an illustration that these two can vary independently. You can have variable absolute timing and quite precise relative timing, and vice versa. You could have two things that are quite precise, but there's no relative timing. That is, they drift against each other, like two clocks that are slightly out of sync. Their cycles will not really could keep a particular relative timing. Any relative phase runs between them would be possible. So this relative timing is often assessed by what's called relative phase. You could say a relative phase would be the distance in time in percent of the cycle time. You can just do it this way, or you transform this to degrees, because the periodic thing, the next moment you would be in the next cycle. Sometimes you can use a phase variable, which is an angle, or you can do it in radians or so. So absolute timing, we in the laboratory, we ask people to follow metronome. For instance, this so-called continuation paradigm, where you ask people to follow metronome, and then you suddenly turn the metronome off. Actually, if I ask you to do that, you tap, and you follow, and I stop, then spontaneously we'll go a couple of cycles more. Because actually what you do when you do tapping and you follow a rhythm in tapping is not that you're reacting to every sound, right? If I say beep, 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 and you're tapping, the delay between the beep and the tap would be way too short for you to actually do that. You're anticipating when the next beep is going to be. So you're synchronizing, synthesizing a periodic motion that you're actually actively doing. So in the laboratory, we're setting this up and then turning off the metronome, telling people to continue. And then we can see how well they can keep that frequency. And people are pretty good at that. I think I have a slide here, yeah. And so they can do that within about 5% of cycle time. So this can be, if you do 1 second cycle time, then this is a bit faster than that. That would be about 50 milliseconds or less. You can go about 20 milliseconds. So quite good. You can also train to do that better. There is a characteristic effect of variance. So the more, if you measure the variance in absolute time, then it increases with cycle time. In other words, it tends to be more constant if you think of it in percent of cycle time. So if you make a very slow rhythm, then the variability is going to be larger in absolute time, not smaller in percent. It's an interesting fact to understand. We made a model actually that explains that. And that is sort of delimits the range over which we can do timed movement. So when you're a human, we would say when it's a couple of seconds, then it's not very well timed anymore. A lot of variance. And actually what people do is maybe they count, that is, they have another periodic process that's faster, and they try to do many of those to do the slower one. They're losing some of the properties of that. And then the fastest movements, it's just physically how fast can you make it do movements, and that's also limited. We can do the fast movement will be down to about perhaps 200, 230, 200 milliseconds, depending on what kind of limb we're looking at. There are cases like drummers who are using mechanical resonance, right? So they're not actually making the movement in detail. They just give a little impulse, and then the stick is reflected off an elastic membrane, and that creates higher frequency. So it's not really that they are modulating the creating a movement, the fully creating movement. And they can go faster than that. So it's actually a bit limited, more limited than one would think. It's about 1 order of magnitude that you can vary the frequency. We actually believe that that has to do with the brain. It's a costly thing in the brain to create time courses. Yeah, I don't want to go. So where do these limit cycles, right? I just throw them out for the robots. These robots guys actually took the idea from models of animal motion, namely so-called central pattern generators, that are models of the spinal cord of animals. So most of locomotion was studied in actually low-level animals, and sometimes even in cats and some animals like that, or rats and so on. And you find that they have neural groups that spontaneously make rhythms. They're called central pattern generators. Spontaneously meaning you can almost cut them off from the brain, well, some limits. And you can also actually disconnect them from the limb. So even if they are isolated as a nervous group, they can produce these rhythms. And so it's the idea that creates some oscillators. And these oscillators, no, because empirically, because there's noise, they are stable, so they must be attractor type solutions or limit cycle. So a stable limit cycle is the generalization of fixed point attractor to periodic attractor. And in this paper, which I'll give you an access to, we look at those as mathematical objects. In the tutorial, you had the Hopf-normal form. So this is the simplest equation in a polynomial sense that has these periodic solutions. In this case, you can transform this to polar coordinates. You might remember where the amplitude has this pitchfork equation. So you get a non-zero amplitude when the alpha is positive. And then you have a phase, which is just the rate of change is constant. And the phase means, sinus of that phase is the solution. And so the constant equation, the solution is a linear function. So you get a sinus function or cosine function. You can have any phase, initial phase. So it gives you a periodic solution. And this mathematically is a stable solution. That is, if you start off the limit cycle, you're going to be attracted into it just because the amplitude gets attracted there. There's a lot more mathematics here. You can ask whether the phase itself is stable or not. I don't want to go into that. So this is sort of the language which people have modeled these neural oscillators. And this language actually explains a lot of the properties of human rhythmic motion. So in this picture, so this is a so-called neural version of that. This equation that is in the winter semester. Actually, this equation is studied a lot. This is sort of the population level description of excitatory inhibitory population of neurons that are very common in the brain. And they tend to have these oscillatory patterns. They are not harmonic type oscillators. They're what we call relaxation oscillators. That is, there are fixed points that are almost stable. You're going to the fixed point, but when you get close, you find it's not stable. Then you go to another fixed point and so on. So I don't want to explain that in detail. There's actually a simulator for that online, but I don't want to go there. So these kind of models can actually account for some of this observed stuff. For instance, in those models, the variability of the cycle time increases with the cycle time, just natural, just off the bat. In a sense, when you have a longer, in any limit cycle, there's an unstable direction. It's actually a marginal stable direction where you have Brownian motion. That's along the limit cycle. So if your noise puts you a little further, then you just keep going. You don't go back to the old time, just keep going further. There's noise. That noise sort of shifts you along the limit cycle. Imagine if you have a longer slower movement, you have more opportunity for such perturbations, and that creates this increase in variance. The longer the movement is essentially Brownian motion, for those who know that diffusion law, Brownian motion, Einstein, that kind of story, for those who know that. Good. So that's absolute timing. And these oscillators that the autonomous roboticists use are inspired by that idea that you just need some oscillator that now you're driving the system with. And because it's a stable oscillator, it will mean that you don't have to precisely plan everything. If you're a little bit off, you're going to go next cycle, you're going to be closer. Now, they're also using the idea of coordination. And human movement tends to be coordinated. So, locomotion, we're clearly alternating. We are bipedal. So for us, of course, you could do hopping or alternation. So it's clear that there's a real constraint on not falling over. If you're a quadruped, it's already a little bit more flexible. And there's actually some subtle stuff where sometimes dogs will make an extra step with one of the legs called relative coordination. And centipedes and so on. So actually always studied. And there's also intralimb coordination. That is, there's a characteristic relationship in the timing between the knee and the hip or the different muscles and so on. And speaking, it's actually incredibly coordinated that way. Concretely, what I mean is, for instance, if the tongue is a little slow to reach the roof or a d, then the roof will also, in its movement, let's say the tongue needs to meet the teeth for some TH, let's say. Then if the tongue is a little slow, then you will also slow down the movement of the jaw so that they still meet at the same time. There are actually rigorous experiments like that where you perturb, for instance, the jaw or the lip. You have a little mechanical device here, and while you're talking, suddenly this device puts on you. That I was a participant in one of those studies in Haskins lab 20 years ago. And you'll just keep speaking. It's too fast for you to notice anything. and you're compensating automatically to, stay close to what you want to do. For instance, really funny things, you pull down your lip and your upper lip will come down to still meet the lower lip, even though if I ask you to move your upper lip down, you probably wouldn't be able to do it. But somehow it works if you do it automatically. And in fact, it's even, it knows whether you're trying to say bab, where you need bilabial closure, or you're saying baz, where you don't. When you do baz, it doesn't come down. It's kind of amazing. It's very flexible. So there's much more there. Just, it's just scratching the surface of a lot of complexity that's there. Good. And I mentioned mastication, chewing, because that's actually also is amazing. Sometimes you bite yourself and then you notice how subtle that is. And that's why you're not supposed to eat while you speak, because it's very difficult to coordinate all of that. You're moving around stuff in the mouth with the tongue, right? And this has to be so that your tongue retreats just, not to be bitten, just at the right moment. And then, of course, the music is like that. And these are roughly rhythmic skills. Speech is actually quite rhythmic. You can actually study that and synchronize your speech with a metronome. And masturbation tends to be rhythmic. Locomotion is rhythmic, but you have similar signatures in non-rhythmic movement. I think I have a slide about that. For instance, when you reach, there is coordination, and that's an interesting case. So when you reach, you open your hand, and then you approach, and you close your hand, right? And this opening, closing, actually, you could even start with your hand open, but we don't do that as students. And so this opening and closing of the hand is coordinated with the transport, for instance, in the sense that if you, while you're trying to do the reach, you're suddenly putting the object further away, then will people also slow down the open? Even though you could say, oh, I'll just open and then wait, I'll have contact. That's what your robot would do if you program it, right? No, it's actually coordinated. That is, you will then also slow that down so that you're still having the same relative timing of the approach to the open. And to do that bimanual tasks are like that. Catching and intercepting is like that, where it's not coordination between different effectors. It's actually between a perceived object and your effector. And here's just an example. When I have this bottle and I move it here up and down, and there's something subtle. You can actually even under certain conditions you can observe it yourself. So what will happen is that if I move this up and down, there will be more of a risk of slipping, right? The tangential force is going to be larger when I accelerate it from down to top, right? This acceleration phase versus the other phase, and you spontaneously will actually modulate your grip force in time with that movement. You just do that, right? And you can enhance it because we're so good at not breaking stuff and compliance. That is just use the right amount of force. And so that is part of that optimization, that we grip it hard only when we need to. And so there's very subtle coordination. In fact, you could say we coordinate movement always. Engineering, you have to do it on purpose. We actually always do that. There is actually a question if there's any non-coordinated movement, and I'll come to that. So before I do that, I want to just formalize. All the time I said we coordinate. What does it actually mean? It's actually a bit fuzzy in the literature. But what certainly the theoreticians, and I'm one of those, mean by that is that there is an actual maintenance of active maintenance, in the sense of stability generation of the relative timing of the components. So separate from controlling the extent of the movement, the where you go, the action trajectory in space, that the time course, so when you are at peak velocity, when you are going to be at contact, that you stabilize that in the sense that you're, have a restoring of the correct timing. If you overshoot, you go, back. If you undershoot, you go forward. Over and undershoot in time. But and I mentioned that speech work. So in human movement, there is actually only one class of movement that is not time. So we time everything, even when it's not necessary. You can see that by the fact that we can actually synchronize with music pretty much every movement. The only one that we don't time normally is locomotion. Like the walking we studied, right? When you walk somewhere, You arrive when you arrive, right? You don't keep the time invariant. You can do that actually, but it's a more macroscopic planning-based thing. For instance, when you catch a ball and you have to run, you know, this baseball or something, when they run right there, they have to time that. In fact, they do that. For instance, they also have this tendency that they don't run there and wait for the ball, that they actually arrive just in time. So when the ball is slowed down, they slow it down, which wouldn't be strictly necessary. But so we can do that. And you see that sometimes when people walk, like when a small child walks with an adult and then falls back and has to sort of catch up, you know, so that you can do that. Actually, some people, some sort of psychological thing when you walk with people, whether they can adjust their speed to you. And some people are not so good with that. So psychologists interpret that in some ways, whether you are, you know, sensitive to that. But this is sort of the limit case where it's not obviously time movement, but everywhere else we time movement. So I mean by timing that thing of controlling the timing, and coordination is a wrinkle of that, right? So even to the metronome, I might control my timing in the sense of noticing that I'm falling short and keeping the time invariant, you know, compensating. But in coordination, that becomes obvious because I can perturb one component and see the effect of the other component. So in the theory, there is this model. So this coupling that I mentioned earlier is actually the mechanism to bring about coordination. That's why the oscillator picture is so strong. And I remind you of an experiment. This is something I did many years ago, or I was involved in, that serves to study that. And that's a phenomenon you find pretty much everywhere in biological motion, that there are two forms of coordination, essentially in phase and anti-phase, or synchronization and syncopation. And synchronization would mean that corresponding movements are arrive at the same time. So for instance, this here would be in phase syncopation in the sense the flexion movement of these two muscles, right? They happen at the same time. And this here, for instance, would be alternation because the flexors alternate. And, you know, gallop would be roughly, actually, it's not perfectly in phase, right? Jumping would be. And then the trot, you know, or walking, it would be alternation. And there are little wrinkles of that. And it's already, so there's been a lot of thought that these are the fundamental patterns because you have essentially excitatory coupling between neural populations. They would tend to synchronize, or inhibitory coupling, and then they would tend to alternate. Turns out that is it's a little bit more subtle. For instance, a famous experiment, one done here in Germany, where you look at this pattern. This would be in phase, right? And that will be anti-phase. And now they turned it around this way. And it turns out this is the pattern that is more in phase. Like, and I'll say in a moment why that's the case, where it's spatially the same as this one, but it is actually anatomically the other way around. We'll come back to that. So we have to study what does that actually mean in phase. So there is a phenomenon that Scott Kelso documented, and I was involved in some of that work, where the anti-phase pattern tends to be less stable. And we mostly use this to show that stability is a property of these patterns because it can be lost. So you find that, for instance, that if you do the anti-phase kind of thing, and you ask people to increase speed, then they lose it at some point. Of course, people might just stop moving then. And so, because you know, something that they can't do it. So you have to tell them, keep the metronome, you keep moving with the metronome. So even if the phase is okay, right? And you can make that they don't see the phase and so on. So there are wrinkles on there. But if you do that right, you find that they switch from antiphase to in-phase as you increase metronome. A lot of these experiments were really done with the fingers. That's a good thing because the fingers are very mechanically very simple and they are not moving a lot of mass. You know, when you do this with your leg, there is actually an experiment where people did this with their legs and they're sitting on a chair and they're moving the legs. But the legs are mechanically so heavy that it's just also mechanical coupling. It's, you know, the whole body sways, and so you can wonder: is it neural control or is it? But the fingers are really just neural. And an interesting thing is that this is this work that we did. You find you can study the muscles, so it doesn't really make any difference. So what you find is that as you increase the frequency, you switch. This is an example, right? We're measuring here. This is the original cycle. So these peaks here are just where the peak position is. The dashed line is of the other finger. And you see they are alternating, and then here they are in phase, right? And from left to right, we increase frequency. You can measure the relative phase in some way, and then it switches from antiphase to in phase. And the interesting thing is there are indices of instability. So here is an example. This is a participant who does that movement, and there is a little torque inserted into one of the fingers. Literally, you have the fingers it's like a manipulandum, and there's a motor on it, and occasionally the motor pulls away your finger, right? And quite strongly, actually. It's kind of awkward. It doesn't hurt you, but it's kind of strong. And you see that the velocity is a bit perturbed and positioned a little bit. And there are some ways how to assess how long it takes to return to the correct phase. And here, for instance, it took about 1.3 seconds. And here it only took about 400 milliseconds. And this is the in-phase pattern, and that is the anti-phase pattern. So you see already with the naked eye, the anti-phase is less stable, takes longer to get back to it. In fact, what you find experimentally is if you increase the frequency, then this relaxation time increases with frequency in the antiphase until you switch. And actually, if you look at another measure of stability, is the variance, just the variance in time. That also increases. Here's some data. This is some data from participants. So different participants look a bit different, but they all have a very clear pattern. This is the antiphase here on top, and that's the in phase. At higher frequencies, the cycles are shorter. And so if you think it's just a question of needing one cycle, you would actually be faster at high frequency. So it is clearly some control effect. So these are signatures of stability. I didn't really elaborate so much on that. So if you do a model, I'll just say that here, a model where there is some attractor at an in phase, this is phase, and that will be in phase, that will antiphase. And if the attractor becomes unstable, so the slope goes to 0 until this becomes a repeller, right? You would be familiar with that kind of bifurcation. Then the stability is predicted to be lost. So the slope becomes flatter slope, less stable. And you predict that the variance then increases. This is something we didn't really study. You can get intuition why that's the case. If you have a steep dynamics, you have this amount of noise, then it would shift the dynamics up and down, and the fixed point would be moving within the small range, and that's where you would be driven. If you have a flatter dynamics, you have this same amount of noise, the attractor now moves a lot more. So it's a bit more complicated because also the slope is different, but so you maybe not moving as fast to the attractor, but overall it works out that way. That's why you're predicting that the variance increases with time. And similar for relaxation time, you're predicting the relaxation time directly is, remember, this exponential minus alpha t, that alpha is 1 over the slope. So these are predicted from these kind of models. So that's why this was very exciting. So that really means that antiphase, it's not a question of not having the neurons to do antiphase. It's a question of they are outside the stable regime. So you won't see it because of that. So that was actually quite influential why this paper is still cited sometimes. Because you can say, that means timing, relative timing requires stability properties, now not a heading direction, now of something like relative phase. And it's coupled oscillators that do that. So if you take oscillators, this is an example of the neural oscillators, and you couple them, which just means that one shows up in the equation of the other. So for instance, here the oscillator number 2 shows up in the equation for number 1, and the oscillator number 1 in the equation for number 2. It turns out it doesn't really matter exactly what kind of coupling you have. That coupling tends to stabilize either in phase or antiphase. And if you change the sign of the coupling, you get the other pattern. And it's more question about how to get the two patterns and so on, which I don't want to go into. So this picture of coupled oscillators is sort of what autonomous roboticists took from animal motion. And it's not all from this human experiment, from older animal experiments. Kodicek worked on locomotive patterns in models of such patterns in animals. So we built actually a demonstration of this in intercepting balls. So we made an oscillator that would be just doing one cycle. It wouldn't do a periodic movement, just as one cycle. It's based on taking an oscillator, a Hopf oscillator, and turning it on and off just right, so that it only does one cycle. And then after that cycle, it would go to a fixed point. And by doing that, we can then synchronize it with some sensory information about a ball. It would intercept the ball. And explain all the equations. So there's an example where there would be a signal that starts the oscillator, and the oscillator moves just on a single cycle, right? This is, it does look like a periodic motion, but it is, it's a single cycle of periodic motion, because when the movement has ended, we're turning off the oscillator. And we were able to show that it can take a ball and even have sensory information about the ball, but it would just make one movement for intercepting the ball and then moving back, and it's stable in some way. And we actually demonstrate that on a vehicle. So this would be an example of a vehicle that does do that timing. So it's the vehicle is this thing. It has a cable because it's a little mobile robot, and the cable is so that you can use the offboard computer, and it would be moving to a target, and then we would introduce an obstacle. And what we arranged was that even though the obstacle forces it to go a longer way around, we compensated by going faster so that it would arrive at approximately the same time. Well, how complicated dynamics that was achieving that. I mean, so this would be an example of timing, using the timing to control relative time. It's of course a toy example, right? It would be like the basketball, baseball guy who arrives in time even though he has to. Actually, I don't think baseball guys encounter obstacles, but yeah. And there is much better work of that line, many years later by in Haute Billard's group in Lausanne, who has these very impressive demos where a robot catches a flying object. And inside there is somehow that principle. I mean, it's actually a lot more things. Imagine you have to estimate the object, track it, and the object will be tumbling, and then you'll have to plan your grasp and do the inverse kinematics and so on. All of that is done. It's it's much more complex thing. I don't even want to explain it, but I have this. Let's have a look at that. I think this is a link, perhaps, no? Can really, this is she wrote a book which I think is also kind of online, or it's maybe illegal. I don't know. I actually own that book. Oh, actually, I want to see that very beginning.
We teach a robot how to predict
Because
a
now
moving
it's
object.
talking, but
After that, we teach a robot where to grasp and how to move each arm.
I think the main novelty we bring to
Which was not defense. Yeah.
We teach a robot how to predict.
It's really,
to
I mean,
move
that actually didn't.
I think the main
100%.
novelty from a human to the
I
robot.
just want to show you.
We call this programming by demonstration. We do not have to explicitly.
This robot interacts with human inhabited environments where
So-
things can change in a fraction of
So
seconds.
she actually
And so they need to
started
be
out
able
studying
to
human.
leverage
She worked in a
a very
human
fast
lab.
computer and a very fast
She
motor
did
that drives
her
them.
and did all the
And
graceful
for that,
stuff.
you need to have controllers that can adapt.
Again, they wrote a whole book about it, so it's a little bit more than I can cover in 5 minutes. But the core idea is still that same kind of idea of using an oscillator and coupling it appropriately to sensory information. Okay, almost done. So this is our version of that, which was about the same time, but much less impressive because it's the robot wasn't very good. But we just simplified that to just the core problem. So it's better than what I just showed. So we used a ball here. I'll show you the robot in a moment. So this is what the robot looks like. It's a ball intercepting a ball. And it was also done because the robot was so poor that it couldn't really move fast. It was not a very good, not easy to control. So we made it slow by making the ball move. So let's first look at what we did there. So we have the ball, and the robot had to intercept it at a certain point with the racket and give it a movement. The movement was sort of one standard movement that would push it up. Again, we couldn't hit it hard because of the robot being so not easy to control. We couldn't give it a lot of accelerations, so that the ball was only mildly pushed up and then in the slow incline. Made everything slower so that the controller could catch up. And it was literally interesting. I showed you earlier that inside there was an oscillator, and so we had to do two things. We had to tune the oscillator to have the right. First of all, we used that oscillator to get to the right location, and also on top an oscillator for the hitting. And to get the right location, meaning just in time. Again, we could have gone there and waited, but we had that idea that we would do that. And so the oscillator was coupled to information about the ball. We estimated the time to contact from the ball, from the velocity of the ball, can be done. And then we also turned on and off the oscillator by neural equations. So this is what is discussed in the winter semester. Some of you may know that the condition of satisfaction and intention nodes, and there's some kind of logic of what a sequence of things, like move there and then make this movement and go back and couple, and all of these are eliciting oscillators for different phases of movement. And so the cool thing about that is that it is exploiting on these stability properties that the system can react to perturbation. So for instance, it can react to a perturbation that just requires updating. So for instance, this would be an example where the ball goes up this incline and comes here, and the arm goes from this position to that position where it does the hitting movement and then goes back to baseline. That will be a clean act where we make sure that it arrives here in time at that position and then triggers the movement in time to hit the ball. And then here's an example where we would inflect the object. So we have a little obstacle here, and that as it is approaching, you see the robot is planning to intercept the object here, but because of inflection, it's shifted there, and the robot can update its target position and the timing to be at the new position when it's within range. And this is a demo. This is the obstacle, and here, see, it's very short here in the robot. See, the initial phase, it's moving toward a point more here where it's moving to the right, and then it updates. So because of originally it's expecting it to hit the baseline here somewhere on the right. It's just a very short time. So we slowed it all down to make that visible. And this is another aspect of that where, again, this is the baseline, and then we would have the ball hit an obstacle and then therefore go away. So it stops actually assuming that it's coming down. So it aborts the movement. That's this neural dynamics I didn't explain. And then the ball ends up coming back and it starts a new movement. So what the robot does is initially wants to intercept, and then it decides the ball is not coming, aborts the whole movement, goes back to baseline, and then makes a new movement. Here's the demo. So as the ball comes, it now goes back to baseline and does that. So in the demo, it is just impressive because just very small movements, but in terms of the underlying control logic, it is really that thing of having behavioral organization, abandoning different movements, but also tuning the movements always to the input. So it's not a fixed movement that's planned, right? It's an equation that can couple. Right? So that is really the conclusion for timing autonomous robots, that they do that as stable oscillators, limit cycle oscillators, and their coupling that makes timing and relative timing. And you can do that for discrete movements as well. It's really just a limit cycle oscillator that you turn on. That you turn on to initiate the movement and turn off at the end of a single cycle. That's sort of the story. And that is actually a model that we are also proposing for human movement, where we have some activity. We actually have it all done. We just need to publish it about human movement, avoiding obstacles, reaching for targets, and so on, sequences of such movements. And it's based on neural populations driving the spinal system that has some reflexes as well, to achieve a single movement, but it has these timing properties. Good. So timing is this just-in-time kind of thing, right? That is the property of timing. That is, timing is control. That's what it calls timing. And so in the nervous system, everything is timed, and There's online updating that I just showed. That is, you can correct your timing to adjust to moving things. You can coordinate across different movements and coordinate with dynamic environments. Now, what's special in biological motion, unlike the robotic motion, that the control is also part of it, right? In robots, we said it makes this time plan, it can also adapt, but the control is separate, just as this arbitrary. Well, in the human arm, you will see next and last lecture that the control is quite sluggish. And so to get the control level to do this right, you actually have to anticipate. And so your timing plan has to take into account control things, not anticipate even more to already say, oh, now I really have to send a signal so that in 100 milliseconds, the muscle will have engaged and something will happen. And we'll come to that. Okay.